Hello there. Welcome back to the Free Science Channel Artificial Intelligence Lecture Series. In this video, I'm going to teach part 2 of Adversarial Machine Learning, which is an advanced chapter in Artificial Intelligence Lecture Series. As I said before, the knowledge of deep learning is a prerequisite of this course. I hope you enjoyed from part 1 of Adversarial Machine Learning. In this video, I'm going to teach the mathematics behind the adversarial machine learning. Hope you enjoy it. Well, I'm going to turn off the camera and start teaching. In the previous lecture, we have learned that one can easily create samples which are in input space and very similar to the validation data, but with very divergent prediction scores. You remember examples from Panda, which was misclassified as a given by adding a small perturbation, and also traffic signs. One was clean stop sign, another one was hand engineered the stop sign, and also the banana picture, which was misclassified by adding a hand engineered sticker to the banana. This shows that the AI systems seem to be capturing on features and making decisions in different way than human does. Also, the idea of adversarial examples show us that our classification systems are not robust enough. This is a significant problem because today's design of the life critical systems are based on machine learning algorithms. Therefore, we need to make sure they can't be easily fooled by an adversary. We have some learning outcomes for this lecture. After this lecture, you should be able to explain the idea behind of the adversarial examples and also explain different approaches in adversarial attacks. You should be able to explain why the adversarial attacks against machine learning algorithms happen. And I hope you learn how to use mathematical expression to describe the adversarial examples. Okay, let us start with targeted and untargeted attack. As you know, the artificial intelligence systems are very powerful in numerical optimization. They can deal with big data. For example, you can feed a collection of data to the network. Here we have collection of data, which is generally called input. Every single item of this data has a label, and this is introduced to the deep net, and we expect the deep net perform classification for us here. But before that, we should train the network. For training, we have a function here, which is called loss function. Loss function is responsible to calculate the error of the input data. To calculate this error, is performed by adjusting the network parameters. How adjust the network parameters? We should calculate the gradient descent, and for gradient descent, we should calculate the gradient per each layer. And by iteratively repeating this procedure, we see that the error of the training per training step, which is called epoch, decreases. Yeah, we get this profile from error of the input data. Then we can say that, yeah, our network is trained well and is ready for classification. Okay, now our model is trained well and is ready for classification. We introduced an input. Input is a picture of the dog, and the network classifies it as a dog with a high accuracy. The idea of adversarial attack is doing the same procedure, following the same procedure, just to trick the classifier. To this end, we add a perturbation to the image, and we trick the classifier, and instead of minimizing the loss function, we can maximize it and increase the score of any other classes. For example, here you see that I have added a perturbation to the image of the dog, and then it is introduced to the network, and the network fooled, and network prediction was cat with high score. And this happens by maximizing the loss function for that specific class. Let's look at the mathematics of this work and see how it is possible. Suppose that we have a classifier f. F is a classifier, and the dot in the bracket means it received the input. The classifier is pre-trained network, and this classifier can perform multi-classification. We have an input x. If we feed input x into the classifier f, this classifier with high accuracy can predict x as c. Here, c is the original class of x. Class of x. Let's say it is dog. Then we added a perturbation to the x. Perturbation here is the epsilon, and we want to the network, the deep net, to classify z as a, which is not c. Let's say a is a cat. And we should bear in mind that these changes, the perturbation that I showed here, is imperceptible changes that human cannot recognize it. To fool the network, we need a while loop. This while loop received z at step t0. What is z0? Z is x plus perturbation. And we ask the network to increase the score for input z for a specific class of a. To this end, we need to compute the gradients with respect to a for the input of zt, and then calculate the gradient ascent for a specific class of a. We need gradient ascent because we need to have higher score of class A. Remember that the original class is C, and we said it is dog, and we need it to be classified as A, which was cat, which is not original class. Therefore, here we need a gradient ascent. And about the alpha, we should have small steps just to avoid make it visible differences. We take small steps of alpha. Alpha is the parameter that we use here. For untargeted attack, more or less the same procedure. We have a input x, and which is classified as C. C is the original class of the X, and we need just misclassification. We are fine with misclassification. Therefore, our target is the score, the classifier classifies Z as I, and I is any class which is not equal to C. The score of any class of I should be larger than a score of class C. For this, we need to calculate the gradient descent for an original class. Therefore, we use minus sign, shows the gradient descent. and we calculate the gradient with respect to the original class with input z, and try to minimize it. It means that we need a step in a direction which minimizes the score for FC and maximize the score for FI. Also, we can describe it like this. For untargeted attack, we can say we have a classifier X and we have input, we have a classifier F, and we have input X, which is classified X, classified as C. C is the original class. For any class except C, we need a gradient, which is called GT, and we should increase the score of other classes which are not C when we input ZT to our model. And here I use the I, which means any other classes, and we are not thinking about any specific classes. Then we need to calculate, we need to have gradient descent for our original class and gradient ascent for other classes. You see that here we have a minus sign. The result of this expression will be ZT minus alpha gradient FC when we input ZT plus alpha gradient FGT input ZT. Here we have gradient ascent, and here we have gradient descent. And alpha should be small enough to not make visible differences. Now the question is, why adversarial attacks against machine learning algorithms happen? Let's walk through an example. I have a training set of some O's and X's. O's are marked with the pink color here, as you see, and X's are marked with a light blue. And I want to make a classifier that recognizes O's and X's. Let's say I have a classifier, I have a simple classifier. For simple classifier, let's say if I have a linear classifier and plotted like this, it is that red dashed line that you see. And maybe I miss some data in the training, and I cannot classify with a high accuracy. Therefore, I prefer to use a more complicated classifier that could classify my data with high accuracy and maybe using more parameters. Let's say I have a classifier that can easily fit the training set. So for this classifier, everywhere that the classifier believes there is an O, so it plots a line and separate this solid line is a classifier. It plots a line and separates O's from X's. And this classifier, this solid line, is an important one, which is plotted by our classifier. And after plotting this line, I can say that my model is trained well to separate O's, which are in the right side, most of them, and the X's, which most of them are in the left side. There is an O near the training set of O's. This O, I mean, I marked it by, it is marked by blue. And to show that this point maybe could be adversarial. And also there is an X here, which is marked, this X, which is marked by red. And And also, this X could be an adversarial. Here in the picture, you see that the blue O and the red X are very close to the training data and how easy they can mislead the classifier. At the first glance, you may say that the reason of the adversarial attacks is overfitting. But if the overfitting was the reason, then we could say that each adversarial example is more or less the result of the bad luck. Therefore, by using different models, we expect to get a random mistake. However, there are adversarial examples that different models misclassify them and assign the same class to them. Therefore, mechanisms that adversarial examples work with looks more systematic rather than being a random procedure. One important reason that makes the adversarial attacks possible is neural networks usually map the input data into the high dimensional space. Here in this picture, you see the CNN, architecture of the CNN from this reference. Just as an example, if we calculate the feature spaces, the feature maps at this layer, just by timing 14 by 14 by 512, we see that we have 100,000-ish. We have about 100,000 feature spaces. It means that at this layer, we have 100,000 dimensions that we can move along them. If we have just one input data, we have 100,000 dimensions that we can move along it. Imagine, usually in the usual cases, we have more than one data. Let's say we have thousands of input data. By adding more input data, we will have more dimensions that we can move along that. To give a more intuitive example, you can look at this figure, which is reported by Roman Novak and et al. At this reference. Here, we have decision boundaries before training at left and after training at right side. I said that the neural network maps the input to the high dimensional spaces. And since during this mapping, the similar images should end up close to each other, most of the training data are mapped onto a narrow region around low dimensional space. This means that outside of the zone with dense training data, the decision boundaries are not properly specified. Look at the boundaries at the left side. More or less, you can mark them. Some of them are very small, but the condition at the left side is much better than the right side, which is after training. And you cannot show a clear decision boundary here. You see that the boundaries are getting smooth. Therefore, many directions in high dimensional feature space exist, such that a small step moving left, right, up, down in this region, in this space, can lead us outside the zone of the training data. This is a drawback that, if we can say it is a drawback, this is and the attackers use it, and you see that how simple is selecting an adversarial example to trick the classifier. To wrap up this lecture, you have learned the targeted versus untargeted, black box versus white box, imperceptible versus perceptible, and digital versus physical, and specific versus universal adversarial attacks. Also, you have learned how to write the targeted and untargeted mathematically. We showed that if we call C as an original class of the input X and we have a classifier F, by making a Z which is very close to the X, we calculate the gradients with respect to A by inputting the Z, and then we calculate the gradient ascent for a specific class, which is A. This is called targeted because we are moving toward a spatial target, a spatial label. But in untargeted one, we just define a GT and maximizing the score for any class I which is not C, and we calculate the gradient descent for the original class and gradient ascent for other classes, and the DeepNet misclassifies the input. Also, we reviewed that how the network maps the input data to the high dimension and by moving epsilon up, down, or left, right in any direction, moving up, down, left, right in the after training, we simply can go out of the training data zone in the space that the training data is not dense enough. And you see that how simply we can select an example from that space and treat the classifier.